Hello and welcome to N24 Predicting Products. This part of chemical reactions tends to sometimes give students, headaches and cause craziness, but again, it is doable if you just follow, a systematic kind of process. So, again, don't need to write these steps down per se. It's kind of straightforward. If you're given words, turn them into formulas. When we write our compounds, these are ionic compounds. We do the crossover method, the crisscross with the charges. Easy enough. Gotta pay attention to diatomics. If you start or end with one of our diatomics, you need to make sure you have a subscript of 2. Remember, diatomics, the mnemonic device, horses need oats for clear brown eyes. Looking at the reactants only, number 2, will identify the type of reaction. So we've seen the 5 types of reactions and their general formulas. We need to relate it to that. Once we know the type of reaction, then we can predict what the products will be. Again, creating neutral compounds, crisscrossing our charges from scratch. That's a big thing. We start over with the ions to make new compounds. And again, remember the diatomics. And then at the end, once the reaction is written, then you will balance the equation. Questions on these steps? Okay. So we got to ask ourselves, does the reaction actually occur? And not all reactions are going to happen in real life. We can write a reaction of what we think will happen, but it doesn't mean that it's actually going to happen. There are so many things, so many other factors into if it's going to happen in real life. But for us, we're only going to worry about these 2 things below, the activity series and solubility rules. Both of these are in the reference section of your notes or on the website, and you will need them. Here's a copy of the activity series. Don't copy it because you can just print it out. It's pretty simple. These are all metals. Metals can replace another metal if they are above the metal that they are replacing. So it's kind of a top-down approach to using the activity series. Any metal that's above hydrogen, so lithium all the way down to lead, can actually replace hydrogen in acids. Meaning, if I were to put copper, which is below hydrogen, with hydrochloric acid, nothing's going to happen because copper is below. And then metals from sodium upward, so notice those are kind of the top left, if you will, of the periodic table. They can replace hydrogen in water. So if I throw some sodium into water, you get a nice little explosion and make sodium hydroxide and hydrogen gas. So again, pretty straightforward in this chart. You look at one metal, the singular metal in the equation, compared to the metal in a compound. If the singular metal is above the metal in the compound, the reaction will occur. Questions on the activity series of metals? Okay. Now, the activity series of halogens. This one you don't need to print out because it's literally on the periodic table. It is the same order as they are listed on the periodic table. So, same idea. Halogens can replace other halogens in a compound if they are above the halogen they're trying to replace. So, for example, we take sodium chloride plus fluorine. Is fluorine above chlorine? Well, on the chart, yes it is. So, I get my products, sodium or chlorine and fluorine switch, and I'm done. Another example, magnesium chloride with bromine. So I ask myself, is bromine above or below chlorine? In this case, bromine is below chlorine. No reaction can happen. So that's all you write, is no reaction. You're done. Move on, stop at the question. That's straightforward. Any questions on this? Okay. All right, solubility chart. This one's a fun one. So This has to do with ionic compounds. As you can see, a bunch of ions, and it's pretty straightforward. You take one or both of your ions that are in any given compound, and you look at it on the chart. Notice in the always soluble, the alkali metals, column 1 of the periodic table, if any of those metals are bonded with any other ion, it will always be soluble. Within your ionic compound, you only need one ion to be considered always soluble, and it will always be soluble. Now, notice we have generally soluble and we have generally insoluble. To the right, we have some mnemonics. So if you look at generally soluble, chlorine, bromine, iodine, chlorine, bromine, and iodine are soluble except for AP and honors courses. Right here, AP and honors courses. Again, A for Ag or silver, lead, and mercury. Fluorine is soluble except when you watch CBS at night. CBS PM, like the channel CBS, and PM meaning night. Ha ha ha. So it's things like that. You'll be able to use this chart, or I will give it to you on an assessment, but you got to know how to use it. Now, what's the goal of the chart? Well, if something is soluble, notice at the bottom right-hand corner, it means it's aqueous. That's its state, or AQ. If something is insoluble, that means it's solid or forms a precipitate. So, for example, let's take sodium oxide. Sodium is always soluble. We see that oxide is generally insoluble. But notice with the exception, oxides are generally insoluble except if they're bonded to alkali metals or ammonium. That's why sodium oxide is soluble. Let's look at magnesium hydroxide. Well, it's insoluble. Hydroxides are generally insoluble, except when they're bonded to an alkali metal or, ammonium. Well, magnesium is not an alkali metal or ammonium. Therefore, this compound is insoluble. Any questions on using this chart? Okay. All right. Going through some practice ones here. On predicting products, we have sodium plus oxygen yields something. So step 1 is write this in terms of formulas. Okay, notice oxygen has to be diatomic. If you forget that 2, it's going to screw everything up. So what type of reaction does this look like? Hopefully you came up with synthesis, A plus X, or A plus B. Well, I need to predict my products. So if it's A plus B gives you AB, then I put them together. But here we have a problem. When you create your new products, you have to do the crisscross method with the ions. So ionic ions crossover, we don't steal the subscripts. That subscript of 2 in the oxygen on the reactant side does not travel. Only the O travels. So if I crisscross my charges, I should get this as my reaction. And then obviously once it's written correctly, now I can balance it and I have my overall reaction now written correctly. Questions on this? Okay. Number 2, sodium chloride breaks into its components. Okay. So sodium chloride, arrow goes to something. What type of reactions does this look like? Well, something breaking apart. Got to be decomposition. Simple enough. So I get this, but hopefully you see a problem. The problem is we have a diatomic. Horses need oats for clear brown eyes. Got to put a 2 there. Now it's written correctly. Now I balance it, and then I'm finally done. Questions on this one? Okay. Number 3, aluminum is added to lead 2 nitrate. Okay. So write this as formulas. aluminum and lead 2 nitrate. Again, you know your ions. You should be able to do this part. Now, looking at the reaction type, what could it be? All right, well, hopefully we figured out it's single replacement. A plus B X equals AX plus B. All the letters are the same. I think I used A and BC or A plus BX. It's the same thing. Now, since it is single replacement, I have to look at the activity series and ask myself, is aluminum above lead on the activity series? Well, you don't have it printed out right now, but I'll just tell you, yes, it is. So because it is, this reaction will occur. Now, let's look at aluminum. Does it make a cation or an anion? Based on its location on the periodic table. Okay, makes a cation. We know that one. So, again, I know the general formula for a single replacement reaction. A plus BX gives me AX plus B. So if I do that, I get this, but we have a problem. On the product side, you have to make sure you do the crossover with your charges for all ionic compounds. By doing that, notice I should have a subscript of 3 on aluminum nitrate. Now my reaction is written correctly. Everything is balanced individually. Now I have to balance the overall reaction, and I have my completed reaction. Questions on this one so far? Okay. But we are not done. When it comes to single replacement reactions, we have to pay attention to the solubility rules. And this is for single replacement reactions. So, we have to think about phases. We know that aluminum is a solid. We can look at lead nitrate on the activity series. Nitrate is always soluble. We know that lead by itself is a solid. And then we have aluminum nitrate. Again, we know that nitrate is always soluble. So my overall equation from a phases perspective should look like this with my states. Any questions on how we got our states? Okay. The next step is we want to make the complete ionic equation. How do we do that? Well, for the complete ionic equation, we are going to take any compounds that are aqueous only. So lead nitrate is aqueous and aluminum nitrate is aqueous. Only the aqueous compounds I will split apart. So notice aluminum is a solid, lead is a solid. That didn't change. Notice the 3 here in lead nitrate multiplied with the subscript of 2 to give us 6 nitrates. Same thing over here. The 2 with aluminum and the 3 with nitrate gave us 6 nitrate. So again, to go from your overall equation to complete ionic equation, we only break apart those compounds that are aqueous. That is an only and that is an always. Only, always aqueous. Now, looking at my complete ionic equation, I have to get rid of these things called spectator ions. Think about when you go to a sporting event. You are the spectator. You are watching. If you are watching the sporting event, do you have any direct influence over the outcome of the event? No, you don't. So you're not participating. In this reaction that we see here, is there anything that is identical on both sides of the arrow? Yes, there is. Well, nitrate and nitrate, there's 6 of them. They are both aqueous. They are identical in every sense of the term. These are my spectator ions. I cross them out. The net ionic equation is everything left over that is not crossed out. When I mix aluminum and lead nitrate, this is the reaction at the very bottom that is actually occurring. The nitrates, they're there, but they're not doing anything. They're just watching. Any questions? Okay. All right, lead nitrate plus potassium iodide. Well, what type of reaction does this look like? Hopefully you came up with double replacement, and we know our double replacement, AX plus BY, gives you AY plus BX. So all of the ions are basically switching. Well, if I do that with the reaction that I've written above, I'm going to get this, but again, I have a problem. When you write your products, you have to rebalance your ionic compounds with crossover of the charges. So by doing that, I should have this. Then, balance your reaction, how you normally balance your reaction with coefficients. And now I'm balanced. Questions on writing the reaction? Okay. However, we are not done. Like single replacement, with here double replacement, we have to also think about the phases to see what's actually going on. So here's our reaction. Now we got to figure out the overall equation with phases. I know that nitrate is soluble with everything. So lead nitrate is soluble. Potassium is an alkali metal. It is always soluble. Lead iodine is generally soluble, except with AP and honors courses, P being lead. So lead iodide is a solid. And then potassium nitrate, again, they're both always soluble. Parentheses don't really need to be there. I wasn't really paying attention, so sorry about that one. So again, to get to our complete ionic equation, all compounds that are aqueous must be broken apart into their individual ions. When I do that, notice everything here breaks apart except the lead iodide. It's a solid. It did not get broken apart. So I have to ask myself a question in order to get the net ionic. Are there any ions that are identical on both sides of the arrow? Well, hopefully you see that nitrate is the same on both sides, and hopefully you also see that potassium is the same on both sides. These are our spectator ions. Remember, they are watching, they're not participating. Well, the net ionic equation is everything left over, not crossed out. Any questions on this one? Okay. Number 5. So, a solution of silver nitrate with a solution of potassium chloride. So, step 1, obviously it might make life easier to write the reaction out. If you can't see it with words, maybe you'll see it with your formula. But again, hopefully, silver nitrate, potassium chloride, that sounds like 4 things. So it's going to be double replacement. If I write it out, silver nitrate plus potassium chloride, and do my double replacement, AX plus BY gives me AY plus BX. Everything's good. Everything's already balanced with my crisscrossing the charges. And then it's already balanced. No need for coefficients. They're all 1s. So it looks like I'm pretty good. Dun, dun, dun. Not done quite yet. Got to think about phases. Single replacement and double replacement are the ones you have to do this with. So please keep that in mind. So here's my equation. I need to look at the solubility rules in order to figure out the states or the phases of everything. Again, nitrates, always soluble. Column 1 metals, always soluble. Chlorides are generally soluble, except with AP and honors courses, A being Ag or silver. So that's why it's a solid for silver chloride. Again, using the solubility rules chart, obviously a lot easier if you have it in front of you. So just something we'll get eventually. Again, complete ionic. Everything that is aqueous break it apart. Only aqueous things. I get this lovely thing. Notice again, silver chloride is a solid, so it was not broke apart. And cross out the things that are the same on both sides. Those are our spectator ions. Whatever's left over gives you your final answer. Any questions on how to predict products? Okay. All right, so this is another way of, I guess, kind of looking at what's going on. They're called particulate diagrams, and we can use color-coded circles, if you will, to represent particles. We know that gases tend to be floating on the top, liquids tend to be, moving around in your beaker, and solids kind of hang out at the bottom. A particle, again, can be an atom, an ion, a polyatomic ion, a compound, a molecule. It can be anything, but it just makes life easier to use one color-coded dot to represent one thing. And then we just come down to use the right numbers of circles. And we draw them to represent the correct phases based on the location of this. So, for example, let's look at aluminum plus lead nitrate. So, we have 2 aluminum that are red. Notice 2 red dots. We have 3 lead nitrates. And then we have 3 leads. And we have 2 aluminum nitrates. So, if we dump it into a beaker, this particulate diagram is actually going to show us the products. 3 leads, you see 3 lead dots. 2 aluminum, 2 red dots. 2 times 3, or 6 nitrates that are blue, notice there are 6 dots. Aluminum nitrate is aqueous, so it should be floating around in the liquid, whereas the solid sits at the bottom. Questions on this diagram? Okay. Let's take lead nitrate and potassium iodide. Well, we have, again, the diagram shows us products. So our PbI2 is at the bottom. It's a solid. And then we have 2 potassium and 2 nitrate, the 2 green and the 2 purple. Questions on how this diagram represents what's going on? Okay. All right, silver nitrate and potassium chloride, giving us silver chloride and potassium nitrate. Again, products only. Silver chloride is a solid that we saw earlier. And then we have 1 potassium, 1 nitrate floating around because it was aqueous. So these diagrams can be helpful to try and illustrate what's going on. All right, let's have you guys try this one. I'll give you a moment, I'll pause it. All right, we are back. So we should have seen that we have 2 silver bromides. There's a red and a blue. There's a second red and a blue. They are solid. And then we have a green calcium, and then we should have 2 nitrates. Any questions on what we got here? All right, thank you very much. Bye-bye.